The 8 is entitled The Coupling of Methane over Promoted Lithium Mixed Oxide Catalysts. It's authored by E. Erekson and A. Lee, and the paper will be presented by Eric Erekson.
Well, thank you very much for having me here and letting me present some of the data that we've, results of what we've done in oxidative coupling of methane. I know that, well, first I'm quite pleased that so many people are here this morning. First, seeing that I was going to be talking on Friday morning, I thought we'd have about 10 people here, and this is very encouraging. And I also feel like I don't need to put a lot of background slides up. I think all of you know what's going on in methane coupling and partial oxidation of methane. But I thought I'd show this slide just to kind of remind you what some of the goals are, and also being someone who works for the Institute of Gas Technology and with people who work in the natural gas industry, we tend to think of natural gas in terms of price per 1,000 cubic feet. But indeed, if you're going to use methane as a chemical feedstock, you might want to think of it. Could someone focus that? Methane right now is selling for about 5 cents a pound. And ethylene is about 31 cents a pound. Now, of course, that goes up and down. Last December, ethylene was selling at about 19 cents a pound. Ethane, a price I got is really for fuel value there of about 4 cents a pound. Obviously, if we make a lot of ethane by coupling methane, we probably won't sell it for fuel value, but we'll put it into an EP cracker or something else that will give us higher value. But I thought that might be an interesting thing to look at. Well, a lot of people are working in methane coupling, lots of different catalyst systems. And here I show just a few, and you know, again, I apologize if I haven't included your system up there. One of the things that we noted early on in our beginning this project on oxidative methane coupling was that basic oxides are kind of the rule here. Most of these are either basic oxides or they're promoted with alkalis. We looked at several systems, but one of the ones that I'm going to be talking about today are mainly lithium on magnesia and variations of that. And looking at lithium on magnesia, you see that lithium is a promoter for this reaction. But it's not an ideal promoter, or maybe I should say it's a promoter that has limits. If you keep adding more lithium, you may get a better catalyst, but that lithium vaporizes or sloughs off with the catalyst so that in the end your stable, steady-state catalyst really doesn't contain all the lithium that you put on in the beginning. So there may be other ways to promote it. So we went ahead with this idea, and I admit it's just an analogy. It's really not much more than that. But we thought, well, perhaps the base strength of the catalyst is a factor in catalyst activity. And not having a lot of experience in making basic oxide or solid base catalysts, we made an analogy to what happens in acid catalysis, where the acid strength of silica is improved by doping with an ion of oxidation 1 less. So the alumina added to silica makes a strong acidic catalyst. Well, we thought if we have a +2 matrix, like magnesium oxide, perhaps we can make what is already a basic solid base a little bit stronger by adding a +3 ion. And so well, I'll tell you about our test and then go on to our results. We did catalyst screening tests. We used about 12 grams of catalyst, a mesh size about a little bit more than 20 mesh. We have about a 1-inch reactor with the thermal well in it, and we have feed gases methane, air, and oxygen, sometimes with air and sometimes with oxygen, but no diluent gas was added. So here's some results. The top line is for straight magnesium oxide, which is calcined and prepared similar to the other catalysts, but we just added water to it and not any other ions. We show the conversion selectivity and a rate. The rate is the standard cubic centimeters of ethane plus ethylene per gram of catalyst per hour. The conversion is the conversion of methane per pass to all products, and selectivity is then of the carbon atoms that react, what percentage of the atoms went to ethane and ethylene. The first line is just magnesium oxide. The conversion, there is some conversion into ethane and ethylene and the selectivity there. If we add just boron to the catalyst, which is a +3 ion, we get a higher conversion. The selectivity is not as good, and the rate is then lower. If we put 1% lithium on the magnesium oxide and no boron, that's the third line, we have a conversion of 17% selectivity, 74%, and a better rate than just magnesium. So lithium is a promoter. Now, if we add both boron and lithium, we have an even higher conversion and a higher selectivity. Now, if boron works, perhaps there are other +3 ion promoters, and indeed we found some. We looked at, well, the first two lines are the data from the last slide, but we also looked at yttrium as a promoter, and lanthanum and aluminum. Yttrium and lanthanum appear to be promoters for this lithium magnesia system. We get a higher conversion, and in some cases, the same selectivity or a little bit lower selectivity. The rates we measure are a little bit higher in those cases. For aluminum, I don't think that we can argue that aluminum here is a promoter over just lithium on magnesia, but we tried that one also. Well, if a little bit of boron works, how much do we really need? Can we put on more? We tried here a range of boron loadings. These are all with 1% lithium on magnesia. And you can see that the conversions go up to a maximum somewhere around 0.2 weight% boron. The selectivity is also highest at that point. And then, of course, then our rates to the C2 hydrocarbons are highest at that point. I think one thing that's interesting here is that we hit a maximum. Well, I guess it's interesting, but it's also discouraging. We were hoping that perhaps we found something that we could continue to increase the activity of our catalyst with. But it appears that there is a maximum, an optimum amount of boron that can be added to the catalyst. I think most of you realize this, but I just thought I'd add it to show that the ratio, this is over a lithium and boron promoted magnesium oxide catalyst, and this is just showing the ethane to ethylene, or rather ethylene over ethane ratio of given product stream. And at lower temperatures, the ratio is much lower. At higher temperatures, we get more ethylene. And if ethylene is the desired product, we'd probably rather work at the higher air. The rates are plotted versus oxygen percent in the feed gas. At about 8% oxygen, that's about 40% air in the feed. We have our first point, and then there's a maximum rate at about 65% air. However, that goes to a maximum, and then at about 75% air and 25% methane, we're making too much CO2, and selectivity goes down, and we're losing activity. However, with oxygen, it has a similar plot, and it goes to a maximum. Here, I show the last point I did is about 14% oxygen. We get higher rates, But part of the higher rates are because we have a higher partial pressure of methane in the feed gas. Now, I have another slide along the same line. Again, the rates of ethane plus ethylene are plotted versus oxygen percent in the feed. The first point, A, is about 8% oxygen. And if you can read these small numbers along the side, I show selectivity and then the ratio of ethylene to ethane in the product. At 8% oxygen, we start out with a selectivity of about 80% to C2 products. And as we go up in rate here, as we're adding oxygen, now in this slide, it's just oxygen and methane. This is not air in the feed. So when I have like 12% oxygen, then it's 88% methane. We go on up to a maximum rate of about 400, but at that point, our selectivity is only 50%. The good news there is that the ethylene to ethane ratio is 2-to-1, so we're making more ethylene at this point. But I think you can agree that in spite of the fact that we're getting better rates when our selectivity is going down, that really isn't the best thing for scale-up and commercialization. Well, we tried another idea along with the commercialization and along with the recycling. We took a feed mix. The top feed mix is assuming that we have start off with about 8% oxygen in the feed and just pure methane, run it through the reactor one time. What is the product mix? Well, the product mix will end up with CO2, ethane, ethylene, and methane, and no oxygen. And oxygen will just about be used up. Well, then if we add 8% oxygen to that and pass it to the reactor again, what happens? And so that's what this first experiment was. However, in this kind of a simulated recycle test or an idea where you have staged reactors, where you have the first stage reactor where you have methane and oxygen fed, and then the product from that reactor is mixed with a new batch of oxygen, you send it over a second stage. Disappointing results from that were that no C2s were produced. We actually consumed ethane and ethylene in the reactor. However, I repeated this experiment with the removal of CO2 from the feed. So just putting ethane and ethylene into the feed as well as methane, we did get some conversion. The rate to C2s, that is additional C2s, is about 59 centicubic centimeters per gram of catalyst per hour. The selectivity is 76%. I might add that at these same conditions, for just methane in the feed, the rate is over 200, about 250. But this shows that there is a little bit of recycle that is possible. Well, at the beginning, I made an analogy to acid catalysis. I was saying that by adding +3 ion, maybe we can increase the base strength of the oxide and get a better catalyst that way. Using some Hammett indicators, I looked at both my lithium boron magnesia catalyst and just the lithium magnesia catalyst. With increasing base strength over to the right, we see that the lithium, with the boron, we get some color change on the catalyst with 2,4-dinitроaniline. With just lithium on magnesia, with that indicator, we do not get any change. So there is some kind of perhaps some better, more base strength with the extra promoted boron. Well, using that same indicator, I showed here for several catalysts whether an indicator was changed or not. With the boron, we have violet. With yttrium and lanthanum, and also with the increased amount of boron, we have some violet color change, but not as much. With aluminum, we have no change, and with just boron on magnesia, we have no change. And that can kind of be understood that, back in the data I showed you for those catalysts, they are not as active as lithium boron on magnesium. Now, I would have liked to stop right there and just say that perhaps I made a more basic oxide catalyst, but the plain magnesium oxide, whether it's just a powder as it comes commercially or the magnesium oxide as we calcined it and so on, it turns dark violet, so that at room temperature there's just the plain magnesium oxide is more basic than our promoted catalyst. And I'll say a little bit more about that as I go through these observations. We found some +3 promoters for a lithium magnesium oxide system, and the surface base strength is increased over lithium magnesium. However, at least at room temperature, we don't see that we've increased our base strength over magnesium oxide. And I don't know at this point, going into this, I felt that that increasing the base strength of the catalyst was the way to go. That was kind of the answer to getting more activity. But I think that in looking at some of the work that the indicator work that I did, I think that it may not be only base strength, but perhaps there's a particular kind of oxygen site that is promoted with the boron or other +3 ions, and not just plain base, just only base strength. We optimized the boron promoter, and we showed that oxygen enhances the rays, and a little bit of recycle is possible. And just wind up with the acknowledgments. I'd like to acknowledge the Gas Research Institute and the managers Howard Meyer and Pete Barone, who've overseen some of this work, and discussions I've had with others at IGT, Kate Martin, Sherman Shaw, and others. And